Yeah, started. Okay, so we started with this Ax equal to 0, and we talked about column spaces, row spaces, and also came to know about a new space called null space that contains the solution x to Ax equal to 0. So how does that work? So if Ax equal to 0, so this A contains several rows of the row spaces. These are the X, and actually we do row multiplied by this column is equal to 0. So that is what is same as this particular equation, X transpose Y equal to 0. So that is what the row space and the null space are perpendicular, and that is what we write it here. Then we came across this particular orthogonal matrix. This is one of the famous orthogonal matrix, which is otherwise known as the rotation matrix. Now, if you analyze each column of this, so X transpose X is equal to 1, and for both the columns it will be the same. And Q transpose Q is also equal to 1, the identity matrix. Now, we were trying to explore something more here, like we had point 1 0 or a vector 1 0, and this is what we rotated by an angle theta. So this is what the value it becomes. What is that? This is equal to cos theta sin theta. This is also similar to, okay, before I go to this theta by 2, let me, yeah, what happens if there is another vector, um, let us say, sorry, 0 comma 1. What happens to that? So that also gets rotated by an angle theta. So that also gets rotated by an angle theta. Okay. So this vector also becomes cos theta minus sin theta, cos theta, 0 1. That is equal to minus sin theta and cos theta. Now, this is what about the rotation is. cos theta minus sin theta, cos theta. Now, similar to this, there is also another matrix, and that is what we're going to see today. Similar to this, there is also another matrix known as the, sorry, yeah. Similar to this, there is also another matrix, uh, cos theta, sin theta, sin theta minus cos theta. There is only a little bit of difference between these two. Mm, yeah, cos theta, uh, yeah, cos theta minus sin theta cos theta. This is what the original rotation matrix is. Now I have just switched the minus sign. At, in place of writing it minus sin theta, I have written it minus cos theta. So what exactly this becomes? What exactly this becomes?
So Q
This is
transpose. Oh no.
uh, that is not Q transpose exactly. This is Q. Q transpose would be this, cos theta sin theta minus sin theta cos theta. But here I am writing something different. I am writing minus cos theta. Now, first of all, let us talk about this orthogonality of this. Let me write this one as mm, uh, let us say Q R, QR. So, what about QR, Q transpose? The same thing. Let us try to figure out here the way we have figured out Q transpose Q equal to I. Yeah, whether you write Q transpose Q or Q transpose doesn't matter. Let me write Q transpose Q. We'll come to that later on. That doesn't matter actually, but for the sake of symmetric, let me write in this way. So how much this becomes? Cos theta, sin theta, sin theta minus cos theta, cos theta, sin theta, sin theta minus cos theta. So that is equal to, is that I? Is that equal to I? Cos square theta, that is still equal to I, right?
Yes, sir. Yes,
Yes,
sir.
sir.
That is equal to I. So one thing for sure that uh, whether I write QR or Q, both are orthogonal. Both are the orthogonal matrices. So whether I write Q or QR, both are orthogonal matrices. Q, we talked it about it as a rotation matrix. Okay, and you will be surprised this QR is actually a reflection matrix. Reflection. So the same point, uh, the same point, I can get it using cos theta, sin theta, sin theta minus cos theta 10 is equal to cos theta sin theta. Isn't it? It is the same point. So one thing for sure that this rotation and reflection about the origin by an angle theta for the vector 1 0 aren't the different. They are the same. But then what about for this 0 1? The rotation about the origin by an angle theta for the vector 0 1, it is minus sin theta cos theta. But what about the reflection? The reflection has to be, it is something like, look at this particular red line, this red line, this red line. Here, actually, we are rotating the point 1 0 and getting this particular point. And essentially, if you see, you are actually halfway the red line, and from red line another halfway. So that is actually the theta by 2. And the same thing if you draw for this vector 0 1, that would be something like um, somewhere like this. It would be. So this is the vector. This may not be looking exactly the same, but then this is the vector halfway through. Yeah. So this is what the reflection matrix is. But then why these are so important? Why these are so important? Can I can I get any, can I prepare, I mean, any random matrix and call it as a transformation matrix like this, what you call this, reflection, rotation, and all this? That is not possible because they have to hold certain properties. And one of the biggest property these matrices they have is that they do not cause any kind of underflow or overflow. Yeah, what is underflow, overflow? Let me deduce it. Let me deduce it. So, what is QX? What is this? Q is one of the orthogonal matrix and X is the vector. So, X vector we are actually transforming through this orthogonal matrix Q. It is very much like this 1 0 vector we are transforming through the orthogonal matrix cos theta minus sin theta cos theta, or cos theta sin theta minus cos theta, or any uh, any orthogonal matrix. So what exactly is this? This we write it as Q uh, X transpose QX transpose QX. So, and I need not say that QX transpose is equal to X transpose Q transpose and multiplied by Q transpose, sorry, not transpose, Q X. And what is this? This is nothing but I, X transpose I, that is the identity matrix X, and which is nothing but X trans X, which is nothing but so look at this. The vector X subjected through this orthogonal matrix Q, you get the same vector X. It's not the vector actually, the length of the vector. That is what this norm means, right? The length of the vector. So vector X, length of the vector X subjected through Q is equal to the length of the vector X. So that is, these matrices, orthogonal matrices do not cause any change in length, or uh, they do not result in overflow, underflow. That is what I said earlier. They preserve the length. Yeah, that is a very scientific statement. Orthogonal matrices preserve the state, preserve length. This is what is known as the biggest property, and the proof of that is this. This is the proof. Okay. So we talked about uh, two number of orthogonal matrices. One of the generic orthogonal matrix, I mean this reflection matrix, is actually the householder's reflection. Uh, there was a mathematician called householder. So householder reflection. It starts actually with the uh, the identity matrix U transpose. This is equal to 1. And the generic form of this householder reflection is Hn, that is for the nth order householder reflection. The equation is I minus uh, 2 times U transpose. This is also written as I minus 2 by n once n. This is a typical MATLAB statement once n, where this actually means uh, if I write 1 3, this actually mean 1 1 1 1 1 1 1 1 1. Okay. So let us see one example. Um, let us see one example like what is H? What is H transpose H? That is actually equal to H square, right? H square. So how do I write this? I minus 2 times U transpose square. That I can write it as I square equal to I minus 2AV 4 times U transpose plus um, plus 4 U transpose U transpose. That I can write it as I minus 4 U transpose plus what is U transpose? That is equal to 1. So that is nothing but 4 U transpose, which is equal to I. So it's square, everything, whatever you take, that still becomes I. So if I talk about, let us take the third order householder reflection, H3 is equal to,
Hello, sir.
yes,
So U transpose equals 1 or U transpose U equals 1?
what did I write there?
On the top of a HN, you have written U transpose equals 1.
No. This is wrong actually. U is a column matrix. This is a row matrix. Column matrix, row matrix cannot be one. It has to be a matrix, right? So this is actually transpose. This is correct, isn't it?
Yes.
Now this is correct. This is correct. Row times column, that becomes a scalar quantity. Yeah, that's a mistake actually. Yeah, third order householder reflection. 1 1 identity matrix, 1 0 0 0 1 0 0 0 1 minus 2 by 3, 2 by 3 once, that I'll write it as 1 1 1 1 1 1 1 1 1. So that actually eventually turns out to be 1 minus 2 yeah, how much this one would be? This one would be something like this, right? 1 upon 3, 1 minus 2, this minus, if I take common, this becomes 1 minus 2 minus 2 minus 2 1 minus 2 minus 2 minus 2 1. Yeah, that's it. Now let us go for the fourth order, and there is an interesting matrix with this fourth order actually, H4. So this is again I minus 2 upon 4, 1 1 1 1 1 1 1 1. Okay, so how much this becomes? This actually becomes 1 minus 1 minus 1 1 mm, yeah, and yeah, please find it out how much it becomes.
Sir, 1 minus minus 2 is minus 1. How 1 is coming?
Hello,
Sir, here how 1 is coming? There is minus 1, no?
which one? Can you be clearer, please?
Sir, 1 by 3. H3 equal to matrix.
H3. Yes.
Sir, 1 minus minus 2 is minus 1, no?
1 minus minus 1 minus 2 is minus 1.
You write only 1.
So in the diagonal, he's saying in the diagonal.
Okay, okay, okay. This one will be minus 1. That is what you were saying?
No, sir, it would be 1 only. We are subtracting 2 by 3 from 1, na?
So 1 minus 2 by 3.
Sir, correct on the side. Previously I have written.
Yeah, it is correct.
1 minus 2 by 3, that is 1 by 3. And 0 minus 2 by 3 is minus 2 by 3. Okay, what about the next one?
So H4 take 1 by 2 common, all diagonals 1, remaining all minus 1.
Yeah, please tell me. Let us continue.
Take 1 by 2 common, sir, all diagonal 1s and remaining all minus 1s.
Diagonals will be 1.
Non-diagonals minus 1, 1 by 2 common, sir.
1 upon 2 common. Diagonals will be 1 and non-diagonals will be minus 1. Okay. Okay. Now, this is householders. There is also another gentleman. There was another gentleman called Hadamard. He also came up with some orthogonal matrices. One of them is 1, 1, 1, minus 1. Okay, this is Hadamard. Don't get confused with, I'm using the same notation H2 for second order Hadamard. For the fourth order, this actually becomes H2, H2, H2 minus H2. The same thing, huh? Look at this. All in place of 1, I'm writing H2, H2, H2. In place of minus 1, I'm writing minus H2. So this actually becomes 1, 1, minus 1, 1, 1, 1, minus 1, 1, 1, minus 1, minus 1, minus 1, minus 1, 1. That is what is your H4 is equal to.
Sir, in H4, all the diagonals are positive, right?
Again, I repeat the same thing. That was householders. This is Hadamard. Just a minute. The presentation is off. Yeah. Householders and Hadamard. Don't get confused with that.
Okay, so got it.
Now, the beauty of this is you just go on increasing this one. H8. It's again H4, 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 minus H4. And that's how it works actually. And it has got a lots of utility in wavelet theory and not many things. you want to the short time Fourier transform, from there the wavelet, and all those, it has got lots of utility there. So like that things continues. We have lot many such matrices are there, and but then the bottom line remains the same. Ax equal to b, that what we started right in the very first class, and will continue to do so. Ax equal to b, and that is what the row space is perpendicular to the null space. Q transpose is equal to yeah, it is better to write few more properties of, I should have written at the beginning of the class itself. Few more properties of, it's like Q inverse is equal to Q transpose, Q transpose, Q transpose is equal to Q transpose Q is equal to the identity matrix. So what is the meaning of this actually, by the way? What is the meaning of this? What do you infer from here? This is one of the most commonly used matrix, commonly used multiplications that you will be seeing again and again and again and again. But what is the meaning of this? Q transpose is equal to I. Q transpose. So the row of Q and the column of Q transpose, are they not same? So whenever the rows are same, they result in 1, and which is nothing but orthonormal. Rows are same. What do you mean by rows are same actually? This is actually 1. The identity matrix is nothing but right. So when do you get this value? The rows are same, right? And here in this case, the columns are same. So this results in 1, which results in, which is nothing but orthonormal. ORTHO normal. Now rows are different or columns are different. That's equal to 0. Here rows are different. That equal to 0. Well, like that, each and everything in this matrix, algebra, linear algebra, it has everything, has got certain meaning, and the objective of this course is actually to understand, to make you understand all those meanings. So that's all for today. See you tomorrow with something more in the class. Thank you all.